and welcome to today's webcast, PCB Materials, Simulations, and Measurements for 32 gigabit per second. It's sponsored by Keysight Technologies, formerly Agilent's Electronic Measurement Group. I'm Don Toot, editor with Electronic Design. First, some words about your console. If you encounter any technical difficulties during today's session, the first thing to try is function key F5 on your keyboard. That'll refresh the screen. If you need further assistance, click on the yellow Help icon below the slides. To maximize the slide presentation window, press the small green button at the top right corner of it. We welcome your questions during today's event. Just type them into the question window on the side of the screen and hit Submit. We'll answer as many as possible during the Q&A that will follow the main presentation, but there's no need to wait. Feel free to send in your questions at any time. Today's session is being recorded. It will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of today's slides by clicking the green folder icon in the toolbar beneath the slides. Now let me introduce today's speakers. Lee Ritchie is considered one of the industry's premier authorities on high-speed PCB and system design. He's the founder and president of Speeding Edge, an engineering consulting and training company. He conducts on-site private training courses for high-tech companies and also teaches courses through Speeding Edge and its partner companies in public venues. In addition, he provides consulting services to top manufacturers of many different types of technology products. Heidi Barnes is a senior applications engineer for high-speed digital applications with Keysight Ease of EDA. Past experience includes over 6 years in signal integrity for ATE fixtures for Verigy Advantest Group and 6 years in RF microwave microcircuitry packaging. She joined Keysight and Technologies in 2012 and holds a Bachelor of Science degree in electrical engineering from Caltech. Alfred Neves is the chief technologist at Wild River Technology. He has 31 years' experience in the design and application development of semiconductor products and capital equipment design, focused on jitter and signal integrity analysis. He's been involved with the signal integrity community as a consultant, high-speed system-level design manager, and engineer. So, and his bachelor's degree is from the University of Massachusetts. So let me turn things over to the first of our speakers. Lee, the floor is yours.
Good morning. Let's see, where are my slides? Don, can we get slide 1 up here for me? Okay. All right. Well, I am participating here because I've sat on the review board for track 5 for DesignCon for 7 or 8 years, reading papers on simulation and correlation, and have noticed over and over that people are frustrated that simulations don't correlate with measurements, and I'm going to, with this section, give you some reasons why. It has to do with how we specify what we want a fabricator to build for us. Let's see, is that advancing? Yeah, let me see. So this first point, how do I make this screen larger? There we go. Okay. If you want to have repeatable, predictable simulation and fabrication results, there is far more knowledge required of materials and fabrication than most of us are used to. It's not something that is an option. What makes the next point come here? All right. I apologize. I'm getting used to this. Many of the disconnects I see between simulation measurements have to do with failure to understand and control the variables that are involved in production of pin circuit boards. So I'll give you an overview of those issues. There's going to be a much more extensive explanation of this at DesignCon. We are collapsing a 3-hour work into 1 hour today, so for more detail, come see us at DesignCon. And again, it's been mentioned already. I'm starting with the materials part of this seminar or webinar, and Heidi and Al will do next test fixture presentations, or excuse me, measurements and test fixtures. So what I'm going to cover are these things, and the materials used to fabricate boards. We need to get much more involved in that. We also need to get involved in how boards are made, and I'll mention the methods that are available to us. You need to know how the flow is conducted in a fab shop so you know where things can go wrong and keep that from happening. And I'll show you some of the SI problems that are traceable to how a board was built or how material was chosen. And then I'm going to close with the documentation that one has to prepare so that the fabricator knows what we're asking for. You'll see later on it's much more extensive than is traditionally done. So let's look at the materials available to build a board. There are 3 basic building blocks that are involved in building a board. The first one of these is copper foils that form all the signal and power layers. The second is a material called a prepreg, which is glass cloth saturated with resin which has not been cured. That will be the glue that makes our board stick together during lamination. Then there are cores, which are that same glass resin composite with foil on both sides that has been cured. And that's going to be all the inside layers of our printed circuit board. And there are dozens and dozens of resin systems out there and lots of different glass weaves. And so many to choose from, many of which are not going to do what we want. And every one of these 3 things can have an effect on performance and loss. And failing to control those is one of the reasons we have disconnects. So how are boards made? Well, there are 3 basic ways to construct a multi-layer printed circuit board. The first one is what we call foil lamination. Second is what's called cap lamination. The difference between those 2 is between layer 1 and layer 2 of foil lamination is prepreg, and between layer 1 and layer 2 of a cap lamination is cured laminate. And then the third one, which is the workhorse of cell phones, is build-up or HDI, where there is a combination of both 1 and 2. And of these, the most common and the most economical is foil lamination, and all of us should attempt to get our jobs done with that. There's lots of good reasons to do that besides economics. Here is the process flow, and this is the flow that would be followed with either foil or cap lamination. All your technical information goes to a fabricator who makes all the tooling involved, and then inner layers are formed 2 at a time on pieces of laminate. Those are combined with prepreg and foil, and the whole pile is run through a lamination step, after which we drill and plate and etch outer layers. And there are 2 or 3 places in that flow that SI can be compromised. I'll mention those in a minute. Kind of problems we can get, SI problems we can get with the material choices in fabrication are these. We can have increased loss due to the finish of the copper foil. We can have increased loss due to the way the fabricator treats the foil after it has been run through several process steps. And we can have increased loss due to our choice of laminates. Those are all things that need to be managed. And there's one more, which is irregulators because of glass weave that will cause reflections on a single trace along its length. So here is a look at what part of the data I draw on is, in order to have good data to make choices, I have had to build test boards out of everyone's materials so that I get a one-to-one comparison. And this particular data is for one of my test boards where half of the signal layers were real smooth copper and the half were the standard copper that we will get if we don't ask for something else. And these are 8-inch traces. The only difference is the foil roughness that came from whoever made the foil. You can see the blue line is what's called VLP, or very low profile copper, and the green is reverse treat, which is the standard copper. And you'll notice out at 14 gigahertz, which is 28 gigabits per second, there's 2 dB of difference just because of how the foil was manufactured. This is, there's a couple of pieces of data missing here. I'll fill you in on what that is. This is 2 boards made with the same artwork and the same material at 2 different fabricators. What's missing at the bottom of the 2 graphs is the left one should say 35 dB at 8 gigahertz. The right one should say 40 dB at 8 gigahertz. That is a 5 dB difference and is traceable to how the fabricator treated the copper during the lamination process. Again, at DesignCon, I'll have photos of this so you can see what that looks like. So we are going to have to control how the fabricator does their job to avoid this problem. And this one next is a chart of dielectrics. The same set of test boards was built, you can see here, 6 different laminates, all made with the exact same test board. And the range of loss is significant, where the red one is what most people call FR4, and the top one, which are blue and is the latest out, called Tachyon from Isola. And so you can see if you don't exercise control over the laminate, you get wide swings in what the loss looks like. Here we have a picture of 2 glass weaves commonly used to make printed circuit boards. The one on the left, 1080, has been the workhorse for as long as I've been in the business to make a 3 mil core, or in some cases a 4 mil core. And on the right is 3313 glass weave used to make a 4 mil core. And you can see the difference between the two is in how the glass is distributed across the surface. On both of those, there is a 3.5 mil wire to give you scale of what a trace looks like compared to the weave of the glass cloth. Notice on the left side that 1080 glass, the wire is for part of its length on top of the glass bundle and for part of its length in between. What's going to turn out there is, because the dielectric constant of glass and resin is so different, where the trace is on top of the glass bundle will have a low impedance, and in between glass bundles a high impedance, and those variations are going to cause reflections along the line that are unanticipated, and that shows up as 2 things. One is loss, and the other, outside the topic of today, is this is where skew comes from. And this slide shows impedance versus frequency for those 2 traces on the last slide. On the left-hand side is the 1080 glass. This is one trace running over on the same layer, all same width from one end to the other, and you can see how widely the impedance swings. Where the bounds dead through the middle is 50 ohms, the top line is 55, and the bottom line is 45, which is the typical plus tolerance of a fab shop. On the right-hand side is 3313, which is called spread glass. You'll notice that the impedance is very nearly flat along the length of the transmission line. And so what we have learned the hard way is one of the things you want to make sure always is that your high-performance boards are made from spread glass. Now, the rub is going to turn out to be how do you define spread glass. It's outside the scope of today, but we're working on that one. This is a bit of an eye chart, but this is the minimum data that I have found you have to provide if you want to make sure that you get the board you were looking for. I'm not sure how well you can read it, but you'll notice that the second column from the left calls out the resin system. In this case, it is eye speed. Next column from there is it a core or a pre-preg, and then the fourth column is the exact glass weave with how much resin there is, and you'll notice that the beyond saying 3313, it says 3313 MS, which means mechanically spread. And we found out the hard way there's two kinds of 3313, and the one that is not mechanically spread is not as good as we need. Then moving one more line over is, hang on a minute here, I've called out the copper finish. And you'll notice there is an X there, and at the top it says X corresponds to very low profile copper. Next to that, to the right, is the dielectric constant, and then the next two columns are thickness, where you'll notice that pre-preg before pressing is thicker than after pressing, and this is because the resin in the pre-preg flows into the voids in the two adjacent copper planes. And then I've got a nice little graphic showing you the signal layers and the power plane layers, followed by the copper layer. Something just happened here. Am I still on? Am I still on? Hello?
Yes, Lee, you're still there.
Something weird happened here. And then all the way to the right is the trace width. And notice that there is no impedance call out here. I don't have time to explain why that is, but I will at DesignCon. So I have found the hard way, this is the minimum data that one has to provide if we want to get the same printed circuit board time after time and not have those variations we've been talking about. One of the things I've tried to illustrate here briefly is that your choice of laminates, prepregs, and foils can have a significant effect on the quality of your high-speed signal path. The current practice in fabricators don't account for the things that I have shown you here, and that has, again, a lot to do with why we have correlation problems. There are two other reasons that Heidi and Al will talk about, but these are the ones that you will see stem from how the board was made. So here's the good news. First of all, we need to control these parameters if we want to get repeatable results. Then we've got to prepare documentation that is complete enough so we get what we were looking for. And this last bullet I added because we have allowed fabricators in the industry to change things on our stack up to suit whatever their current inventory is or practices, and that is, to be mild, that's hazardous, so that has to stop. We're bit by bit getting fabricators trained this way, but it's a habit, and unfortunately, I've seen fabricators change things and not tell me, and I get to throw away a lot of boards. A whole other topic that is how do you keep that from happening. That's the basic intro I wanted to put together for set the stage for the next two sections. And this last slide is just contact information, which the intro mentions some of this, and anyone who's interested in more data from Speeding Edge, there's our website. And with that, I think I turn this over to Heidi.
Thank you very much, Lee. That was an excellent introduction here on printed circuit board stack-ups and fabrication. Appreciate that. Now let's go ahead and jump into part two. My focus is going to be on simulations. So multi-layer laminate printed circuit boards are everywhere in today's electronics. One would think that a technology that has been around for more than 50 years would be easy to simulate and measure, and yet for the niche of high-speed signal integrity applications, it is not easy. In part one, Lee Ritchie did a great job in explaining how PCBs are fabricated and the key features controlling high-frequency performance. Now I'm going to demonstrate a methodical approach to achieve stellar simulation to measurement correlation to 40 gigahertz for data rates up to 32 gigabits per second. Here is a very simple printed circuit board structure. You would think that this type of simple structure would be easy to simulate and easy to measure. It is simply a trace or in the case of a high-speed signal, a transmission line with an adjacent return path that defines a characteristic impedance of Z0 equals 50 ohms. In the middle of this trace is a 1-inch section where the trace width is increased by 3x the width of the 50 ohm trace. This is a type of series resonant Beatty standard that is commonly used in verifying the calibration of high-frequency network analyzer measurements, and we will use it here to calibrate our measurement-based models and verify the accuracy of our measurements and simulations. This simple structure provides a calibration in the time domain by showing the stepped change in impedance, and calibration in the frequency domain by showing the resonance of this 1/4 wavelength resonant structure and the frequency-dependent losses. Now let's look at how we can get the simulated Faraday's eye diagram we have here at 32 gigabits per second to match the measurement we took at 32 gigabits per second. It is really not very easy. Why and what is involved? So I've been working with Al Neves for a while with his CMP28 test structure platform, and this is one of the things that he's always saying, that it is really not very easy. But why is this? Getting simulation to measurement correlation to 40 gigahertz for 32 gigabits per second designs is difficult because most engineers do not take the time to follow two basic engineering principles. Verify that the as-fabricated material properties match with what is used in simulation. Obviously, garbage in, garbage out, and Lee Ritchie showed us in part 1 a lot of the items that we need to control very precisely to know exactly what we are supposed to simulate. Secondly, we must verify that the measurement system is calibrated to measure the exact same structure as that we are doing in simulation. Measurements without calibration are not measurements. How to obtain the as-fabricated PCB material properties and how to obtain a well-calibrated measurement reference plane are the two challenges. So the big picture, everything needs to work together. The definition of the DUT, or the structure that we want to measure and simulate, how we're going to connect to that, the fixture design, what type of measurements we are going to take, how we're going to remove the fixture or de-embed it from the measurement, and identifying the materials or the actual structure that is being simulated. So that's the big picture. So let's look at how we want to do this. The reason we're talking about the Beatty standard is that this is actually a very fascinating little structure. The Beatty standard is superior to a single width through line on a printed circuit board. A single width transmission line calibration structure only validates the dielectric constant and losses. The Beatty standard adds a stepped impedance change for gaining information on the as-fabricated etching and PCB dielectric height. You can see here this simple Beatty standard structure. If you look in the time domain of the impedance versus time, as you go through the structure, the first section of transmission line is 50 ohms, but when you approach the 3x trace width, now this wider trace width has a lot more capacitance and the impedance drops to around 25 ohms. And then because of the double reflections, you get a little bit of stepped impedance reflection discontinuity, and then you're back to the 50 ohms on the output. In the frequency domain, you can see that if there were no losses, you'd see the clear resonances of the double reflections here of the forward traveling wave reflected twice and delayed in time and adding to the original wave, creating these resonances. But also, since there's printed circuit board losses, the real measured data or blue data shows this loss versus frequency in the plot on the right. So with this Beatty standard adds a stepped impedance change for gaining information on the as-fabricated etching and the PCB dielectric height with this impedance change. With one simple standard, one can verify the as-fabricated PCB stack-up properties for high-frequency performance and avoid using up valuable printed circuit board space for multiple standards in your design. So there is one problem. I want to simulate the Beatty standard, but in the measurement, as you can see in this picture, I also have the connectors that go from the coaxial reference plane of our network analyzer measuring system to the planar transmission line on the printed circuit board that attaches to our Beatty standard. So what do I do? Here's a simple cartoon of the problem. It shows that typical instrument calibrations are done to the end of a coaxial connector. But the start of our Beatty standard is on the PCB. So how do we remove this coaxial connector transition to the planar PCB transmission line that we call the fixture? To do this, we will leverage the experience of the network analyzer world and the use of S-parameters with a little bit of matrix math to move the reference plane to match with our simulations. There are numerous ways to measure the S-parameter model of a fixture, as well as creating deconstructed measurement-based models of the fixture. Next week at DesignCon with Lee Ritchie and Al Nez, on Tuesday with the tutorial, we will go into more details on this topic. But for now, let us just assume that we have this fixture model, the S-parameters for the fixture. What do we do with this S-parameter characterization of the fixture? And here we have a plot of the loss versus frequency of this fixture, as well as the reflections from it, the return loss. With the S-parameter, this we can use in simulation. First, we can do a bit of matrix math made easy by simulation tools to de-embed or remove the effects of the fixture from the measurement. Here in the upper right, you can see how to de-embed, or you can see that there is a de-embed symbol for the fixture S parameters that is cascaded with the full path measurement. The result shows how the added losses and reflections from the fixture are removed from the blue full path measurement and result in the red trace, which is the loss versus frequency for just the DUT, or the Beatty standard in this case. So in the upper right is the loss versus frequency of this blue path, which is the measurement with the fixture still in it, and then the red path is the measurement with the fixture removed, and you can see it has less losses, and we can see the ripple of the Beatty standard a bit clearer. But there is one critical step to remember. When doing de-embedding, it is important to make sure that the fixture S parameter does actually match with the fixture used to measure the DUT, or the Beatty standard in this case. This is easy to do in the time domain, where one can look at the impedance discontinuities versus time for the fixture model and overlay this with the full path measurement and make sure that those impedance discontinuities of the fixture line up with the fixture connecting to the DOT. Once we have verified that the fixture model matches with the fixture used in the measurement of our Beatty standard, now we can look at the results. By removing the fixture from the measurement, we are getting very good correlation between the model and the measurement out to 40 gigahertz. Here we see a plot of the S parameter of the Beatty standard comparing measurement and simulation, and the loss versus frequency going out to 40 gigahertz. We do notice that there is some variation or divergence out at the higher frequencies. So what is causing that? Now here is a fun exercise to do, and it actually brings us a lot of information. We just talked about de-embedding the fixture from the measurement, but what about if we do not change the measurement at all? We look at the exact measurement that was done with a NIST traceable calibration to the ends of the coaxial cable, but this time we're going to embed the fixture into our simulation. So now we can have a schematic where we cascade the S parameter of the fixture with our transmission line model of the Beatty standard. And what's interesting is the end result now, it looks like we're getting much better correlation, because at the higher frequencies, we're actually seeing that with the full path measurement, the signal is actually rolling off, and potentially our fixture model and our fixture performance is rolling off at those higher frequencies. So here we're getting very good correlation. We're able to predict with simulation, that full path measurement, which is also what we do in the when we actually generate, or let's say measure a Accuracies eye diagram. So by using this methodology, we have calibrated the as-fabricated material properties in our simulations, as well as verifying the ability to characterize and de-embed or embed the fixture from our measurements and simulations. And here we can see at 32 gigabits per second, we're getting a good correlation between our eye diagram for this PRBS9 signal for simulation as well as measurement. So just in summary, what we're talking about here and what we've validated with Wild River's technology CMP28 ADS starter kit and the Beatty standard there, first we need a fixture model. Then we need to remove the fixture from the measured data. We then calibrate and validate our simulation model, our transmission line models, with the measurement of just the DUT Beatty structure. And then finally, we embed the fixture back in with our model and verify it with the full path measurement and gain confidence in both simulation and measurement. So in summary, I would like to say thank you, Mr. Beatty. This Beatty standard is a very quick way of a very simple structure to fabricate and a very simple structure to simulate and measure. So if you're interested in this topic and you want to learn more, please come to the DesignCon tutorial, Breaking the 32 Gigabit per Second Barrier, PCB Materials, Simulations and Measurements, next week on January 27th at 1:30 p.m. Also, at the tutorial, we're going to be going into more detail on how to extract as-fabricated material properties from the Beatty standard, how to get a model of the PCB fixture, and examples of deconstructed measurement-based VIA models. So thank you very much. And now I'm going to turn it over to Al Nez, who's going to provide additional details on the challenges with measurement.
Hello, this is Al Neves. Can everybody hear me okay?
Sounds good, Al. Maybe a little bit louder.
Okay, is that better, Heidi?
Yes, thank you.
Okay, my name is Al Neves. I'm the Chief Technologist at Wild River Technology. Our business is helping signal integrity engineers, and this presentation is a foregleam of a presentation we'll be doing next week as we discussed, and is a work of a collaborative effort on the EDA kit, which is a comprehensive simulation of our platform for both the full path and the de-embedded, as Heidi discussed. So I'm going to hit the yellow button and see if this works. Okay. I'm not seeing the slide update. Can we do a slide update?
You may have to hit function F5 to... Let me go ahead and...
All right. I don't know if it worked or somebody advanced it.
Looks good. Yep. You're on test fixtures for benchmarking.
Okay. So as I said, this was a collaborative effort where we took our channel modeling platform, and frankly, this was, we really had an A team. We hired a contractor to work with us, and this was the result of several months worth of measurements. And what we found out is if I were to be able to pick people to do this project, I probably found the best that you could find, and there were still challenges to do 40 to 50 gigahertz. I'm trying to, can we advance to the next slide? We've been designing these platforms for quite a while, and back when I was a signal integrity engineer, I did quite a bit of work doing platform design. And one of the things that we learned is that one problem, and I'm talking 40 to 50 gigahertz types of platforms that are used for simulation to measurement correspondence. You have to think in a sense of entirety. You have to think of a sense of holism, and everything has to work. The measurements have to be pristine. Your measurement capability has to be very good. Calibration needs to be validated. As Heidi pointed out, the de-embedding is really a challenge when you're doing 40 to 50 gigahertz simulation to measurement. I'll go in and talk to a customer, for example, and I'll say, they'll raise the simulation measurement, and I'll say, well, what are you trying to simulate or measure against? And the team will get a bit quiet. So one of the things that we're hammering in this presentation is you have to be careful what you define the DUT to be, and you have to make good measurements and then de-embed out to that DUT. That's extremely important. The other thing that we've learned recently in the last couple of years is test fixture architecture is really important. I'm going to show an example of that. Moreover, the general signal integrity has to be really pristine. And an example of that is, I'm going to advance to the next slide.
Smile, which slide did you want to be on? Up in.
This is the right slide, 43.
Okay, correct.
Okay, so we're talking about measurements. We're going to discuss measurements because that's one of the key areas. A lot of people have problems with measurements. One of the keys in designing your system is if you're designing a 40 gigahertz system, and we employed this trick, and actually I learned it from Heidi, is we actually measure the system out to 50 gigahertz. And then after de-embedding and simulation, we actually get a usable 40 gigahertz. Often, what I see happening is you make a measurement to 40 gigahertz, and you really only effectively have about 30, 32, 33 gigahertz of bandwidth. So a good, well-designed system will give you good signal integrity past f-stop. Okay. Now, the other reality of measurements. And this has got us a lot in the last few years in using older architecture VNAs. The new architecture PNAs, for example, from Keysight, they're really low noise, and people overlook that. Real S-parameter measurements have noise, and they really create a lot of problems when you're doing the de-embedding, and that's an often overlooked thing, and we'll talk about that a lot in the more exhaustive presentation next week. This is another area that you need to look at is an S-parameter workflow. You make a measurement, it's validated calibration, what do you do with the measurement? And if you don't have a workflow to address the passivity, the causality, you may want to run it through a rational compact type of model or a polynomial and resample it. ADS has that capability, and that has advantages when you're doing time domain. But you definitely want a workflow. And then you want to use standards to validate your measurements. For example, airlines and stepped impedance coaxial standards. So I'm off to slide 44. This is an example. We've had when we started to design these platforms a few years ago, we had problems with connectors, and the connectors are really optimized on the market for. I'm not trying to denigrate anything, but they did market those connectors, most of the vertical launch connectors, to handle satellite military applications. They worked pretty good. Recently, we've developed connectors and custom designed a launch that gets out to 50 gigahertz. And this is an example of using an adapter, a 2.4 to 2.92 millimeter adapter. The launch is 2.92 millimeter, which means you have a 40 gigahertz calibration capability. But once you put a 2.4 millimeter adapter, you can use a 2.4 kit. And if you look, there's two launches here. One is the red, which is the good launch, and maintain 10 dB of good return loss all the way out to 50 gigahertz. So we're really happy about that design. I incorporated some intentionally bad launches and the blue one is an example of a bad one, which is poor return loss, and you can see evidence of that in the return loss in this diagram. Sorry about this. Let's advance to slide 45. We talked about de-embedding. You make a calibration, you calibrate, and that's the first thing that you do, and you validate the calibration, and you have some reference plane. You do de-embedding after you do your calibration. Calibration of the VNA is, everybody does calibration of the VNA, but not everybody understands the two things that it does. One, it sets up your reference plane, and two, it calibrates and reduces the error to what you call residuals. It's really important to understand what calibration does in terms of the reference plane. Even if, for example, you had a perfect VNA, let's say it was the year 2400 and Keysight developed the perfect VNA with no error, you'd still need to do a calibration in order to establish the reference plane. Let's go to the next slide. De-embedding has been a real problem for a lot of signal integrity engineers. And about 10 years ago, the first thing that I worked a lot on is TRL calibration. And we're abandoning TRL calibration as a way of calibrating. It's not really a de-embedding approach. It's really a calibration approach. It effectively will create the reference, will translate the reference plane or provide you a reference plane up to your device. So it serves that function. But you have to make a lot of measurements with TRL calibration. There's a lot of problems with the impedances, and you have to make a lot of measurements. And for multi-mode systems that we work with every day, differential systems, I don't think it's a good approach. The two approaches that we're using are symmetrical calibration. As an example is AFR with Keysight has AFR, and they've talked about that and done quite a bit of application development. That works pretty well. We like that a lot. It gets me an answer real fast. Make a measurement, and it'll bifurcate, and I'll talk about that in a second, and give you two S parameters that you can use to de-embed. We did a lot of development in this, and we'll talk about this next week, on measure modeled. It's a lot of work, but you get a lot of insight into the system. And the accuracy is somewhat comparable to automatic fixture removal. There's quite a bit of work in the measure-based model. It does have some advantages. Of course, the disadvantages is it takes a lot of time, and you really have to understand what you're doing. It's not a simple thing to do to the measure-based model. Next slide. So what you're trying to do when you're doing the de-embedding is you're trying to bring the reference plane up to the device under test. Now, you don't necessarily need to do that. You can do what's called a full path simulation. For example, if you have a model of the connectors and the launches, which we do provide in our EDA kits, you can do a full path simulation. That doesn't necessarily give you insight into the device, and even if the launches are really good, which they are on this platform, you still see some aberrations. It's kind of like, a Hubble telescope versus an earthbound telescope. You're still seeing the atmosphere, so you still have the loss and the minor reflections of the connectors to deal with. But understanding exactly what your DUT is, whether it's full path or de-embedded, as it's shown here for the BD standard, is really important. Next slide. So this, I've run into engineers who are new to this, and I wanted to cover this on de-embedding. What basically you do is you take a structure that's a through, and that has to be designed very consistent with your actual DUT plus your network. So at the top, that's our structure we want to analyze and do simulation measurement. So what we do is we pull off the launches to the left, and then we create a through. So there's a through associated with the actual dot structure. Okay, the next slide. In the case of automatic fixture removal, or any of the symmetrical calibrations, you would measure the through, and the algorithm bifurcates the S parameter that you measured into a left and a right-hand S parameter. And the left hand is used, you either can do it in ADS, or you can do it in a software like PLTS, or MATLAB also works. So you can do this directly in the VNA, or you can post-process the S parameters. I prefer to do it in ADS, frankly, because I like to make my measurements and do an S parameter workflow on the measurement, and then I take the bifurcated S parameter and I use that in a post-processing step in ADS. ADS really handles de-embedding really well, and it's all graphic. It's really easy to use. I like it a lot. I'm not trying to market that. It's just I'm telling you what our approach is. When you go to the next slide. I think somewhere someone's cranking a handle, and it's like, next slide. So in the measure model-based approach, that's another way of getting the S parameter. And what you do when you create when you do the measure modeled, you're not just measuring it through and passing it through an algorithm that bifurcates the S parameter and gives you the left hand and the right hand path. You're modeling the entire system symmetrically, and then what you're going to do is you're going to divide that manually. So you're going to model both the launches, and then you're going to then what you're going to do is you're going to bisect that model. Next slide. Now, when you before you bisect the model, you're creating a model, and what we did in the EDA kits, we did an exhaustive amount of correspondence and matching the model to the simulation both, and I'm only showing the frequency domain here, but we also did it in the time domain. So we matched the model of the through both in the time and the frequency domain, and then we bisected. Next slide, and then we pulled that S parameter in half by what we bifurcated the S parameter by resimulating one half of the left-hand fixture and resimulating the right-hand fixture, and thereby giving us this two S parameters. Okay, you want to go to the next slide, please? One of the things that we've learned that we really like a lot is, everybody wants to design the big system. The big system's on the right. It has lots of connectors, lots of things going on. It's complicated. It's also high risk. We're always looking for ways of mitigating the risk. And one of the things that we've done, which has been real money for Wild River Technology, is we build these small mini platforms. And they're not very expensive to do it. And I don't see people doing this a lot. In other words, design something architecturally that gives you a lot of stuff and do it really fast. The fabrication costs are really low. You can do a quick turn on something like this. You can create a lot of boards, small platforms from a panelized, so you can hand those out to different locations. The companies are all international now. You can hand those out to different locations. And you can get a lot of bite out of something like this for feeding the field solver, and you can do it in real fast time. And that's a systematic way of approaching the bigger problem. So from an architectural standpoint, these little mini platforms are beautiful for doing launch design. You can do material identification, and as I said, it's systematic and low cost. The other thing that we do it for is vendor qualification. I see a lot of our customers waste boatloads of time and money in building these big systems with a new fab house, and then they end up with junk because the fab house didn't get the right drawings, or there was a mechanical or they goofed or something. And these little platforms are great ways of doing qualification of the fab house. Next slide, please. The other thing that we looked at, we did a project this last year, 10 gig project, and it only worked at 20 gigahertz. But I'm going to make a point. This is certainly not a 40 gigahertz type of platform. And what it was is we were evaluating a backplane, and there really wasn't any room to put structures like throughs and other things on these daughter cards. Okay, so what we did was advance the next slide, please. What we did is, and we also didn't know where the reference plane was. The spec is a little ambiguous, whether you're at a connector or down in the transmission or right up to the connector. So what we do is we built and we did this on the same panel. We panelized a companion card. Now, if you look at this, there's obvious things that I wouldn't do if I was doing 40 to 50 gigahertz on this platform. So this is really about a 20 gigahertz platform. But what's really beautiful about this approach is I have a separate independent card that was panelized with the daughter card, so it's the same stack-up materials and so forth. And essentially what happened was, we were able to do a lot of stuff with that panelized calibration card. Okay, so thank you for attending. My name again is Al Neves. We will be at DesignCon. I don't think anybody mentioned this. Heidi and I both are also on a simulation measurement panel that should be, to say the least, quite lively at DesignCon on Thursday evening. And here's our contact information. We're really, for a small company, we're really happy. We're a finalist in Best in Test. And if there's anything I can do to help you, or Wild River can do to help you with your signal integrity needs, please contact us. Thank you.
And thank you, Alan. So now a few of you have already submitted questions, and we'll jump right in a moment. If you'd like to submit a question now, type it into the question window on the side of your screen and hit submit. While we're answering your questions, we'd like you to complete a feedback form. You'll find that at the top of your console now. You can also access this survey through the red globe icon on your widget bar. So jumping right in, if we can scroll back to the actual image on slide 36, the question is, how close in that are the individual ground vias spaced to the vias that are next to them, center to center? Looks like on one side the strip, let's see, if you can answer that question, that would be the start. Who wants to take that?
Al, do you want to talk about that launch design there with the ground vias and the spacing?
Yeah, can you hear me okay?
Sounds good.
Feel free to comment. What happened to the slide? Hello, where's my 44?
Oh, 44?
Is it, what slide was that again? Was
the question from the audience says slide 36.
Oh, 36. So.
But you've got to add the dummy slides ahead of that to come up with the correct answer. So you probably are talking about 44.
Yeah, I think they're talking about 44. Yeah, let me push that one back. Perfect.
Okay. So the question is how do we design the vias? Is that
what's the actual spacing?
I don't know offhand. I don't remember that. The rationale for the spacing, the vias that you're looking at right now are picket fence vias to isolate structures so you don't have reflections from one structure to the other. And that's not just for the launch, but that's for all structures in the platform.
Okay. Part of the question has to do with, are we spacing based on the wavelength that we're looking that we're sending over that signal? A quarter of the wavelength?
For the launch optimization, that's true, but you actually don't see that in the picture. The vias that are apparent in the picture are picket fence vias that serve to isolate structures from other structures. There are vias, however, underneath the vertical launch that set up a coaxial cylindrical cavity so that the energy, comes down and it is mode-free as possible out through 50 gigahertz and with really good return loss. So if people have questions about the launch design and how we set up that, and there's not a picture of that there. The picture of the vias, again, is to isolate structures. I could take those vias and move those further away and move those closer in, and it's not going to change the launch reflection or return loss very much at all.
Okay, a question for Heidi. I'm not sure how to interpret this. Would you add a Beatty standard on every signal in the ZSIBO layer?
Yes, I think that's the intent here is if because you're trying to verify the stack up for that transmission line layer. So ideally you'd have a Beatty standard for each signal layer that you're interested in, where you could maybe cut some corners and reduce the number of test structures is if the stack up is identical in terms of the layering. But to get started, or when you're first initially evaluating a fabricator or a certain stack up, it is recommended that you try a Beatty standard or some sort of standard on each layer so you can verify that the stack up was built according to your fabrication document.
All right, and I think this one is also aimed at you. It's a question about resolving the differences between different PCB simulation tools.
And here I guess I have to fall back on the whole concept of this presentation is, test structures are wonderful, and the simple Beatty structure, if the vendor simulates the Beatty structure and you simulate in a different tool and get the same answer, then you have a lot more confidence in both tools. And it's really about understanding how the measurements are done, how the simulations are done, and verifying those things. So you need a way of calibrating, and the Beatty standard is a wonderful way of doing that.
All right. Is there a reference that compares different glass weavings?
And this one's for Lee Ritchie. How do we know which ones are uniformly weaved?
The $5,000 question. We are working on, first of all, there are no standards yet on how weavers spread the glass, and so we at IPC have a group that's trying to solve that problem. I know by experiment. How's that? Right now, that's all the choice we have, so I guess you're going to have to stay tuned. I build lots of test structures into boards to figure that all out. There's no 15-cent answer to that question.
Okay, Lee, this next question I think is also directed at you. If you use 313 style glass, do you still need to do zigzag routing?
I never do that. That zigzag routing is a solution that was proposed about 10 years ago. It works, but however, it is not practical. Try to zigzag route a backplane that has 5,000 nets on it. It's not practical, and so we are solving that problem a different way. This is kind of, I don't want to be doing a commercial, but ISOL has two new laminate systems that are weave independent that I use because I can't trust the weavers to do the weaving the same way month out, in and month out. So my current fix is a material that is weave independent.
All right, and then we have time for one more question. If a person can't get to the DesignCon to see your tutorial, is there a way to get the slides?
So yes, Keysight will, and we've always done this, is we publish the presentations that we've been a part of on our Keysight website after DesignCon has ended. So please look for emails and links in future or after DesignCon for links to our DesignCon presentation for those of you that are not attending DesignCon. I believe also Al Neves with Wild River will be doing the same sort of thing and posting his presentations from DesignCon on his company website. So thank you very much, and we look forward to seeing people at DesignCon next week.
And I'll chime in real quick. Anyone who would like a copy of my complete set of slides can request it through my website. I won't post it on the website, but you can request it, and I'll send it to you.
Very good. So that concludes today's presentation. On behalf of Electronic Design, I'd like to thank everyone for joining the webcast today. You're invited to attend our next event in the Tutorials on Signal Integrity webcast series. That one's called Super Speed USB 3.1 Physical Layer Simulation for Electrical Compliance and at 10 gigabits per second. That's going to take place on the 26th of March, 26th. So thanks to Keysight Technologies for sponsoring this event for us today. And to everyone out there in the audience, have a productive remainder of your day.